This is a proof that the square root of 2 is an irrational number, and it's one of the 2 formal proofs required on the A-level maths syllabus. We'll begin by assuming square root of 2 is a rational number, and we'll derive a contradiction which will mean our assumption was wrong and root 2 is in fact an irrational number. So starting point, assume the square root of 2 is rational. Now, a rational number is a number that can be written as a fraction where the numerator and denominator are both integers. So we can say, therefore, root 2 is equal to capital P over capital Q, where P and Q are co-prime integers. Now this proof depends on P and Q being co-prime. So let me just digress to talk about what co-prime actually is. Co-prime integers are integers which don't have a common factor. So let's suppose that the square root of 2 was 24 over 16. If that was the case, we could cancel that. We could cancel it down to 12 over 8. But we could cancel that down to 6 over 4. And we could cancel that down to 3 over 2. But we reach a point where we can't cancel anymore. We can't cancel fractions down infinitely. So eventually we can choose the 2 integers to be co-prime, so they have no common factor. They've been cancelled as far as it's possible to do so. So capital P and capital Q, we're assuming, have no common factors. Right, let's get back to the proof. If that's the case, I can square both sides. So root 2 times root 2 is 2, and P over Q times P over Q is P squared over Q squared. I'm now going to multiply up by the Q squared to give 2Q squared equals P squared. Now what can we deduce about P squared? Well, P squared must be even because it's Q squared multiplied by 2, and Q squared is an integer. So that implies that P squared is even. But that in turn implies that P is even, because the square of an even integer is even and the square of an odd integer is odd. So let's call it, say, 2 times little p. So capital P is 2 times small p. So now we're going to say root 2 is equal to 2 times little p over q. And again, I'm going to square both sides. So root 2 times itself is 2. 2p over q times 2p over q, and this is little p now, would give me 4 little p squared over q squared. Now I'm going to multiply through by the q squared again, and I get 2 capital Q squared is equal to 4 little p squared. Now I'll divide that equation by 2 and get q squared is equal to 2 little p squared. But what does that tell us about capital Q squared? It tells us that it's even because it's little p squared multiplied by 2 and p squared is an integer. So that implies Q squared is even. And just as before, that will in turn imply that Q is even. Say 2 times little q. So capital Q is 2 times another integer, which we've called little q. Now if we go back and substitute in the original, we get root 2 is equal to p over q, where p and q were supposed to be core prime, but we now find that that's 2 little p over 2 little q. So however far we've cancelled capital P and capital Q till they were core prime, we suddenly find we can cancel again by 2 to get little p over little q. So this contradicts P and Q being core prime. Therefore, assumption, and there's only one assumption we made, root 2 is rational, was wrong. Conclusion, root 2 is irrational. If a number's not rational, it's irrational. And that completes the proof.